not yet recorded session. Okay, give me a while. I'm going to show you the notes. Okay, I have put the notes on the WhatsApp group, so you can download it there. Okay, so basically, right. So this is the new chapter. So we're going to look into the unsigned numbers, as I just said. All right, and also we're going to look into conversion of data, okay, to any of the form. All right, and explain the unsigned arithmetic instruction on the flag. Okay, and we're going to do some, all right, on the assembly language using unsigned arithmetic instruction. Okay, so we have add, ADC sub, SBB, mul, and division. All right, mul is multiplication and div is division. Okay. Right, so this is in this chapter. Okay, so unsigned numbers is data actually in which all the bits are used to represent the data. Okay, and it applies to the add and sub instruction. So meaning that it can apply to any addition or uh, subtraction instruction. Okay, so no bits are set aside for the positive or negative sign. Okay, so let's say we have between 00 and FF, okay, from 0 to 255 decimal. So you have 256 numbers, okay, from 00 to FF for 8-bit data. And you also have for the 16-bit data, so where you have the 000 to FFFF, okay, from 0 to 65535 decimal. So in that you have to 65536 decimal numbers. Okay, that's for 16-bit of data. Okay, so in order to perform the addition of unsigned numbers, so this is how we do it. Okay, so we add the destination and source. Okay, so this is actually similar to the one that we use for the sign. Okay, and we have another command actually, add an ADC. Okay. Okay, so the destination of the operand, okay, can be a register or in the memory. Okay, that so we have In the register, it is inside the CPU. In the memory, is inside the memory itself. So which is external from the CPU. Okay, so the source operand can be a register, in memory, or intermediate. All right. And memory to memory operations are never allowed in the 86 assembly language. So it must be paired either register or memory, or register with register, not memory with memory. Okay, when we have this instruction, it would change your flag register. Okay. Okay, let's have a look at the first example. So let's say we have this number. Okay, basically we have a 0F. Okay, we have 0F5. Okay, we want to move that to AL. Okay, then what we have, okay, we add a 0B to the AL as well. So we to actually add 0B to 0F5. Okay, so 0, so because it's just 8-bit, okay, because there is no because the 0 on the upper bit is not counted on the F5, so we just take F5 and then we add with 0B. So for F, of course, it will be, if you convert that to the binary number, okay, 10 and 10, so it will be 1, 1, and 1. Okay, so it will be 1, 1, and 1, and number 5 will be 0, 1, 0, 1. Okay, so still remember how to do the conversion. So this is 2, 0, and then this is 2, 2. So this 2, 2 plus 2, 0, so 4 plus 1, so it should be 5. And we have 0B, so over here all of those numbers are 0, and then we have B, so B is 11. Okay, so B is 11, so we have 2, 2, 3, so 8, 2, 2, 1, 10, okay, and 1, right? So that's 11. Okay, so we perform the addition. Okay, once we perform the addition, so let's have a look. So we have 1 plus 1 will be 1, 0. So we bring over 1 over here. So 1 plus 1 will be 0, 1, 0. So 1, 0 over here. And it's still 1, 0. All right. So over here is still 1, 0, and 1, 0, and 0, 1, 0. And then actually you have a carry over here. Okay. So that's why your CF will be 1. Right. And sign. Okay. The sign, the status of D7 result. Okay. So what will be your D7? Okay, your sign will be 0. Okay, your sign will be 0. This depends on the of D7. So you look at over here. Okay. And for PF, okay, parity flag, okay, number of ones is 0. Okay, because it's parity flag, we look at the number of ones. So number of ones over here is 0, right? So there is number of ones, so it is even. So it is even number. So when it is an even number, so that's why we have the parity flag as 1. Okay, and for AF, okay, auxiliary carry flag, we look at between D3 and D4. Of course, it will be 1 because you carry over 1 from D3 to D4. Okay. Okay, once you have that, so your 0 flag will also be 1. So because all of the numbers over here are 0. Okay, so that's how the flag is affected, okay, by the addition of the unsigned numbers. Okay, so this is the program, okay, that you can use actually to apply, okay, but we will look at this later. All right, so basically we can MU8086 to perform this actually to code this program. Okay, so what does this program do is we want to make sure that we want to calculate the wage, okay, the wage of a worker. All right, then this person, okay, does not make more than $255, okay, a day. All right, so whenever the number exceeds, all right, whenever the number exceeds 255, okay, so it won't, okay, it won't, it will be give you some error because we give error because we say that the maximum number, maximum wage of this person is 255. Okay, so you look at the numbers over here, all of those numbers are not exceeding 255. Okay, so the program won't give you error, right? So, but we need to state this condition. So this is the condition. Okay, as we learned in the previous lectures, so we have the flow chart when we can make the decision. Okay. Okay. All right. From there, okay. So okay, we look in terms of number. Okay, we first need to do the conversion. All right, in order to perform the code. Okay, so let's have a look over here. So 125, if you convert to the hash, so it will be 7D 235 0EB. Okay, 197 will be 0C5. Okay, and 91 5B and 48. Okay, so we count that. Okay, so we count that. So we look at the flag. Okay, we look at the flag register. Okay, so over here, if I go back a little bit, I cannot show you the real coding over here. Okay, the full code is in the book, all right? But I cannot show you here. So let me just skip this problem first. Okay, we're going to, all right, to perform the coding as well as we're going to look into each of the line later. Okay. Okay, this is still the example, all right? This is still the example on how we perform the addition using the assigned numbers. We're going to look into the subtraction. Okay. All right. So in subtraction, the 86 processor used 2's complement. Okay, so we take the 2's complement on the subtrahend, the source operand, okay, and add it to the minuend. Okay. And then we need to invert the carry. Okay. So let's have a look at how to do that. Okay. Okay, so right, so we look if okay, after the execution, if CF the carry flag is 0, so the result is positive. Okay, if CF is 1, the result is negative, and the destination has 2's complement of the result. Okay, so this is where we have the sign numbers. Okay, so meaning that we have the sign to that number, so we have positive and negative. Okay, so we look over here. So we have 3F. Okay, for example, we have 3F. We add to the AL. Okay, and then we load the BH. Okay, with the 23. Okay, and then we need to subtract. Okay, BH from AL. Okay, so from there, we need to place the result in AL. So meaning that we take AL and then we minus with BH. Okay, so how do we perform that? Okay, so directly we cannot do the minus. Okay, we cannot do the subtraction directly. Okay, so but what we can do is, okay, we perform the addition. Okay, perform the addition, but by using the 2's complement. Okay, 2's complement. So over here we have this 23 as 0, 1, 0, 0, 1, 1. Okay, and then what is the 2 complements? If you still remember, so we add 1. Okay, we add 1. After that, we add another 1. Right, so that's the 2's complement. Okay, so you have, alright, so you first okay, sorry, you invert the number, you invert the number and then you add with 1. Right, so it will be 1. So from here it will be 1. Okay, so if you 1, 0, 1, 1, 1, 0, 0. Okay, we take this. Okay, we invert that and then we add 1. So it will be 1, 1, 0, 1, 1, 1, 0, 1. Okay, so that's the 2's complement. And then we add that. Okay, so we add this. So 1, 1 is 1, 0. So we still have 1, 0 over here, and this is be 1, 1. 1, 1, still 1, 1. It's still 1, 1, and this one become 1, 0. Okay, this is 1, 0, and then this is 1, 0. And then this will be there, you have the carry over there. Okay, so since this is subtraction, okay. Okay, since it is a subtraction, your CF, okay, is 0. Okay, your CF is 0. Okay, because right, when you perform the subtraction, the results actually give you the positive number. Okay, the result give you the positive number by looking at the sign over here. Okay, but because this is, we are using the 2's complement, so it will be different. Okay, so the flag over here is, you should be actually the original one, the CF should be 1, right? But over here it will be 0 because we use the 2's complement, not the original number of that we subtract. Okay, so CF will be 0 and other flag should be, okay, other flag should be following that. All right, so ZF, okay, ZF of course, because it is not 0. Okay, if it is not 0, and then AF, okay, AF is 0, okay, and PF is still 0, okay, because we consider that that's the number of 1, right? So that's the number of 1. But over here, we have 3 ones, okay, so it is an odd number. So it's considered only even number, so that's why the PF is 0. And the sign flag is 0. Okay. But you need to also note that the thing that changed here is CF and also AF. Okay. Originally, because AF and C is the same behavior, they do the carry. Okay, so they do the carry. Okay, so the carry, as we did here, we take the 2's complement, so CF we consider that as 0 and also AF will be 0.
Doctor,
Yes?
AF actually should be 0 or 1 if we not use a second complement.
For what? For addition?
Yes, for addition. If the result is for D3 and D4 is 1, 1.
Okay, so CF will be 1 if for the addition. Okay? CF,
AF.
AF
For
will also be 1. Okay? Like this one. Okay, previously like this one. AF. Okay, like this one. AF will be 1. Okay? Whenever there is a carry from D3 to D4. Okay?
Doctor, but this is 0, 0, right? It's become 1. But in the example, is 1, 1 becomes 0. Can you explain a little bit? I cannot get it.
Okay, for the auxiliary carry flag, okay, for the auxiliary carry flag, we look at the what we carry from D3. So this is D3 over here, and this is D4. Okay, so we look over here. Okay, so 1 plus 1 will be 1, 0, right? So we need to carry over 1 there. So that's why AF is 1, right? So but this one we don't use the 2 complement. So that's why AF is 1. Okay, and for the carry flag, we look at the after D7. Okay, after D7. So this is the D7. Okay, this is the D7. Okay, this one D7. So we have excess of 1. Okay, so 1 actually you can imagine that it is at D8. Okay, something like that. So that's why you have CF as 1. Okay, so come back to this example. Okay, come back to this example. As we can see that, okay, the result, okay, if we perform the direct subtraction, so you can assume that f is 16, right? So 16 minus 3, so it will be 13. So, sorry, f is 15. 15 minus 3 should be 12. So 12 is C. Okay, 3 minus 2 is 1C. Okay, if you convert this 1C to this number, okay, so of course it will be 0, 0, 0, 1. Okay, and C will be 1. Okay, so this is 2 to the 3. Okay, okay, 2 the 3. 2 to 0, 2 to 2 to 0, 2 to 1, all right, and then 2 to 2, and then 2 to 3. Okay, so we have C is 12. Okay, C is 12. So we have 8 and 4, right? So that is 12. So 1, 1, 0, 0. Okay, so that is similar to 1C. So this is the result that we want. Okay, so when we do the two complements, so that's why it works. Okay, so we look over here. Okay, if we perform directly, okay, if we perform directly the subtraction over here, so we can look again. Okay, it is actually okay 1, 1, 0, 1, 0. Okay, sorry, 1, 1 will be 0, 1, 1 will be 0, 1, 0 will be 1, 1, 0 will be 1. Okay, there is no carryover over here, so that's why AF is 0. Okay, but inverse to the complement, okay, that we made, there is a carry over here. Okay, so the rule is you just need to remember, okay, whenever there is a carry, they will be inverted. Okay, they will be inverted. Okay, so that's why over here we have EF as a 0. And we look over here, 1, 0 and 1, 0. So 1, 0, and then okay, you have 0 and 0. Okay, it is similar result. Okay, if we perform direct subtraction. Okay, but the computer cannot do the direct subtraction like that. So it needs to do the two complement. Okay, so if from ourselves we read that, okay, so we don't have any carry, so that's why our CF is 0, and also we don't have any carry from D3 to D4 as well. Okay, so that's why AF is also 0. Of course the F is 0, and parity flag, we depends on the number of ones, so number of ones over here is odd, so when it's odd then it's 0. Parity flag will only affected when the number of ones is even. Okay, so let's say the number of ones is 0, number of ones is 2, but number of ones is here is 3. Okay, so it's not affected. Okay, and for the sign flag, we look at the D7. Okay, so the
Okay,
program,
okay, okay.
yes, you got
Okay,
it.
yeah, yeah.
Okay. Okay, as you mentioned, the programmer must look at the carry flag. Okay, must look at the carry flag to determine if the result is positive or negative. So actually, it looks at this carry flag. Okay. Okay. some interesting result over here. Okay, so we need to look at the example. So what do we have over here? Okay, so when we perform this, so we have the data of 4C and 6E. Okay, so first we move 4C. Okay, so this is 4C. We move to DH and we subtract, okay, 6E, okay, to the 4C. All right. So we jump, okay, we have the jump instruction. If CF0, jump to the next target. Okay. So we jump to the next target. So mean that if we perform that correct, okay, we go to the next and move, okay, data 3, okay, now DH move to the data 3. Okay. But if CF is 1, the carry flag is 1, okay, then takes the 1's complement and then add increment to get the 2 complement. Okay, so that's the rule, okay, for this program. So we follow this step, okay, so what we have, okay, so we minus 4C to the 6E. So the results actually will be negative, okay, because the number over here is bigger than this one. Okay, so C minus E, okay, so E is much bigger, okay, so E is much bigger, so we need to inverse that. Okay, so E is 14, okay, and C is 12. Okay, so 14 minus 12, you have 2, okay, and 6 minus 4, you have 2, so it's negative. All right, but in the computer, right, so we need to perform by using the 2's complement, okay, by using the 2's complement. Okay, okay, so how to do that? Okay, so as usual, we invert that number first. 1, 0, 0, 1, and 0, 0, 0, 1. Okay, and then you add 1 to this. So it will be 0, 1, 0, 0, 1, 0, 0, 0. So that's the 2's complement. So it is similar to this one. Okay, so you perform the 2's complement, so you add that. Okay, so 0, 0, 1, 1, 0 is 1, 1, 0 is 1, 1, 0 is 1. Okay, and then you have 0, 1 is 1, 0, 0 is 0, 0, 1 is 1, and 0, 1 is 1. Okay, so there is no carry flag. Okay, so you look at the carry flag. Okay, as I said, for the subsection, when we look at the carry flag is 0, meaning that it is a negative number. Okay, so it is a negative number. Okay, so that's why we took a negative over here, and then the result is negative. Okay. Okay, so when the result is negative, and then we cannot actually stop over here. All right, we cannot stop over here. Okay, because this number is not similar to 22. Okay, it is not similar to 22. So what we need to do is to invert back. Okay, to invert back this number to first complement. Okay, to first complement, and then add 1 again. All right. So what we have here is 1 1 0 1 and 1 1 1 0. Okay, so we have 0 0 1 0, and then we have 0 0 0 1. Right? So you have this, and you add 1. So of course you have 0 0 1 0 and 0 0 1 0. So that is 2 2. Okay, so that's how you get the result. Okay, so the meaning over here is that, okay, the CF, okay, over here is 1. Okay, it is inverted, right? And when you look, the number over here is 0. When you do the subtraction, okay, the CF is 1. So it won't, okay, so firstly, it won't happen. When you do the subtraction over here, it won't happen to this, okay? It won't go to next, okay? It is because it is CF is 0, okay? Over here is jump, no carry, okay? So because there is no carry, then it will only jump. But if carry is available, meaning that carry is 1 over here, so it won't instruct this instruction. So it will follow this. Follow this one, then take again, okay? Take again this one, okay? Do the first complement, and then from there add 1. Okay, add 1. Okay, so that's how you do it, right? So once it's CF0, now it becomes back to here, so it becomes back to there, then you can jump. Now you can jump and then store the value. Okay, so that's how this program works to perform the subtraction. So that's the meaning of the sign numbers, addition and subtraction. Okay, so we also have the SVB command. So we also have the SVB command and also the PTR. So SVB is used for multi-byte numbers, okay, multi-word numbers. Okay, it will take care of the borrow of the lower operand. Okay, if the carry flag is 0, okay, SVB works like subtraction, okay, SUB. But if the carry flag is 1, SVB subtracts 1 from the result. Okay, SVB will subtract 1 from the result. Okay, so the pointer data, the pointer PTR data specifier directive is widely used to specify the size of operand when it differs from the defined size. Okay, so we look over here, we have one example. Okay, word PTR tells the assembler to use a word operand. True, the data is defined as a double word. Okay, so we look over here. It is a quiet a long number. Okay, we have 62562FA. Okay, and we have 412963B. Okay, so the word PTR, okay, will take, okay, this 62FA. Okay, word PTR data A put into the AX. Okay, and for the data B, it will take this one, the last 4. Okay, word PTR data B and then the subtraction. Okay, perform the subtraction. So what do we have? Okay, so we have 62FA. So we have 62FA minus with 963B. Okay. So from here, what you look from this number is much bigger compared to this one, right? Okay. So we look at this one. We can also do the conversion, all right? We can also do the conversion to binary number. Okay. So to perform the move, all right? So of course, the sign as we can get here, it will be negative. Okay, it will be negative. Okay, so we need to minus. Let's say we look over here. Okay, so what we have, when we perform the sum, okay, the result that we obtain is CCEDF. Okay, but over here the number is not correct, right? Because we need to invert back. Okay, we need to invert back the number. Okay, into the 2's complement. Okay, mean that we need to invert a number and then add one increment to that, and then we get the subtraction correct. Okay, so but over here, when we use, okay, so what we use over here is we use SBB. Okay, so we use SBB. Okay, so let's have a look. Okay, so this is what we have. So let's do the subtraction. So we have, so for 6, what is the number? It will be 0, 1, 1, 0. And then we have 0. Okay, we have 0 and 0, 1, 0. And then we have F. Okay, F, we have 1, 1, 1, 1. Okay, and A, we have A is 10. Okay, 1, 0, 1, 0. So 1, 0, 1, 0. Okay, so for this number 962B, so for the 962B, the result is it is 0, okay. Sorry, it is 1, 1, 0, 0, 1, okay, and 6 is 0, 1, 1, 0, and then 2 is 0, 0, 1, 0, and B is 11. So B is 11.
Doctor, I think it is 3B, right?
Oh, 3B. Oh yes, it's 3B, sorry. So we have 3B, then it will be 0, 0, 1, 1. And then the last one, B. So B is 11. So we have 1, 0, 1, 1. Okay. So when we do the inversion, right, of this, it will be 0, 1, 1, 0, 1, 0, 0, 1, and 1, 1, 0, 0, and then we have 0, 1, 0, 0. Okay, and you add 1. So of course this will be 1. Okay, so you perform the addition over here. Okay, so 0, 1, 1, 0, and 1, 0, 0, 1, 1, 1, 0, 0, and then 0, 1, 0, 1. Okay. So when we have this, so we perform the addition. So the result will be 1, 1, 1, 1, 1, 1, 0, 1, 1. Sorry. So from here we have 1, 1. Okay, and over here 1, 1, 1, 1 is 0. Okay, and then we carry 1. So we have 3, 1. So we have 1, 1. So it will be 0. Okay, and we add 1. So when we add 1, it will be, okay, at 1 here, then you have 0 again, and 1, and 1. Okay, there's not enough space over here. Okay, I'm going to continue over here. Okay, over here it will be 1, 0, sorry, it will be 1, 1, 1, 1, 0, 0. Okay, so that's the number. Okay, so we have this 1, 1, 0, 0, and then we have 1, 0, 1, 1, and 1, 1, 1, 1. Okay, so this is what we have. Okay, so let's do the conversion. Okay, if you invert this number, so what will it be?
CCBF.
Okay, CCBF, right? Okay, CCBF. Okay, so this is similar like this one. Okay, so we got it correct. Okay, but as I mentioned, this result, so we haven't do the 2 complements back. Okay, we haven't do the 2 complements back. So when we didn't do the 2 complements, then we still not get the result correct. Okay, so let's have a look at the next instruction. So over here, okay, this guy, okay, take the, okay, we have the data 6 to F, okay. He wants to move, okay, this data, okay, with the addition of 2, okay, with the addition of 2. So when with the addition of 2, what happens is that we'll take this number, okay, we'll take this number, okay. So we'll take 6 to 5, okay. Okay, we'll take here, so it will bring to AX, right? And then also for the data B plus 2, so we'll take this 412, okay. So it will take 412, okay, subtract with 2, 6 to 5. 412 subtract. Okay. All right. So for the SPB, it performs the subtraction. Okay. So this is the way how it performs the subtraction. Okay, minus. Okay, you obtain 3, okay, 1 and 2, and then minus 1 again. Okay, that's the function of SPB. Okay, so you have the results of 2, 1, 2. Okay, so what the results that you obtain is that, okay, so AX now, the result from SB is moved, okay, is moved to the world PTS result. So this one is the result for the upper bit, right? For the upper bit. So this is 0212, and we have the lower bit as this one, okay, is CCBF, right? As CCBF. Okay, so I hope it's clear on how you use the SBB and also sub. So the difference is that. Okay, so for the SPB, we see directly the subtraction and then we minus 1, okay, from that. Okay, we're going to look into multiplication and division. Okay, right. So by the meantime, let's have a break for 10 minutes. Okay, we will continue after that. Any questions so far?
No, Doctor.
All right. All right. So let's continue. All right, with the multiplication and division. So we have the unsigned multiplication and division, right? So how we do that? Okay, in multiplying two numbers in the 86 processor, the use of register AX, AL, A, H, and DX is necessary. Okay, the function assumes the use of those registers. So whenever you do multiplication, you need to use these registers, right? AX, AL, AH, and DX. Okay, so we have three multiplication case. So which is byte times byte, word times word, and byte times word, right? So when we have byte times byte, we have operand 1 is AL, okay, which is the lower bit of A, register A, and then operand 2 can be either register or memory. So as I just mentioned, it can be a combination of register and memory, but it cannot be from memory to memory. Okay, so that's why we need to use the registers. Okay, for the result will be in terms of AX. Okay, and for word times word, so we have AX, okay, as operand 1 and operand 2 either register or memory. So we can either have that as the result in terms of DX and AX. Okay, and we also have the last one, word times byte. So operand 1, where we put the byte is on the AL. So similarly as the first example, the first line over here. So we put the byte on AL and AH we set to 0. Okay, and then operand 2 will be register of memory. So the results also be in terms of DX and AX. Okay, so we look at the byte times byte. Okay, for this one, all right, so we look over here. So 25 is moved to AL and then 65 is moved to BL. Okay, and then we do the multiplication. Okay, multiplication to BL. All right, multiplication to BL. Okay, remember that. So for BL, okay, when we do the multiplication, right, so we don't need to specify AL over there, okay, because it is automatically will be stored in the AX as mentioned over here. Okay, when we have the operand 1 as AL, then the result will be stored in terms of AX. So we just move the AX, okay, let's move the AX to the result. Okay. Okay, over here, the register addressing mode was used. Okay. So we also have another example on the textbook as well. Okay, so that's byte times byte. Okay. How about word times word? Okay, so word will be longer, right? So like this one. So which is our data tree is 2378, okay, to AX, right, to F79. Okay, we multiply that. Okay, we multiply with the data 4, okay, to the AX. Okay, so AX is 2378. Okay, and then the results. Okay, we look back over here, the table. Okay, so we have the word times word. It will be to the AX. Okay, AX and DX. Okay, so the result 1, okay, will be the AX and the result plus 2. Okay, plus 2 for the upper upper 16-bit number. All right. So you put that into the DX. Okay, the result will put into the DX. So we need to mention that DX to move that DX to the result. Okay, so for the word times byte. Okay. So we have the data 5. Okay, so this is the 8-bit number. All right. Moving to AL. Okay, and then AH, right? AH must be cleared because AH has the rule that AH must be set to 0. Okay. AH must be set to 0. Okay, so whenever you perform this, you must set to 0. Word and times byte. Okay. Then multiply. Okay, once AH is cleared, then you can multiply with the data sets. So which is the word, right? And then, okay, we move, all right? We move the result, okay? Result 3, okay? We point to the product, okay? Bx points to the product, meaning that we're going to store that, okay? We're going to store that, these results, okay? Into the Bx, okay? So into the address of Bx. So now, okay, as you back to this table, so we have the result into also Dx and also Ax. So Ds and Ax must be stored to the Bx. Okay, so like this one. So we have that Ax and Dx. Okay. All right, so that's the way how you perform the multiplication. Okay, so we look at the division. Okay, similar like multiplication, you also use the register of Ax, Al, Ah, and Dx. Okay, for the division, all right, so you have one more case, okay, which is double word, okay? Double word over word, right? So you have similarly, so for multiplication, you have bytes by byte, but require byte over byte, word over word, right? Word over byte, okay, and we have the double word over word. Okay, so that's for the division case. Okay, when the CPU cannot perform the division, an interrupt is activated. Okay, so the as an exception, the PC will display a divide error message. Okay, okay, if the when this happen is when the denominator is 0, and if the quotient is too large for the assigned register. Okay, so it will give you the error. Okay, so this is the rule. Okay, so byte over byte, the numerator must be in the AL register and AH must be set to 0. And then the denominator cannot be immediate, but can be in a register or memory. Okay, supported by the addressing modes. Okay, so after the division instruction is performed, the quotient is in AL and the remainder in the AH. Okay, so meaning that the result will be in AL and then the remainder will be in the balance or the remainder or the baki, right, will be in AH. All right, so we look over here. When we divide byte over byte, okay, then we have the AL as byte and then we need to set AH at 0. Denominator can be register or memory. Okay, and then the quotient will be in AL and the remainder will be in a AH. Word over word, the AX must be word and DX is 0. Denominator is also all of the denominator can be either register or memory. The quotient, all right, will be, because word by word is bigger, so we use quotient in terms of AX and remainder in terms of DX. Okay, and then we have word over byte. AX is word, so of course, right? So this when it's word, right, then it's byte. So usually we just get byte, right? So we just get byte. So we use smaller register, which is AL and AH. For double word, okay, the numerator will be combination of DX and AX. So we have double word, okay, because it's 16-bit and also 16-bit. So double word. So the word is a 16-bit number. Okay, so we have, the word is 16 is 32. So meaning the double word, we have 64 bit of number. Okay, so once you have that, all right, once you have that, then the quotient will be stored in the AX and also DX. Okay. Okay, you have that. Okay, the divide error interrupt if AL is bigger than FF, and also if AX is bigger than FF. Okay. So this is the various addressing modes of the denominator. All right. So we look over here. Let's say this is the allowable modes. Okay. So this is include the direct mode. Okay, and can also be used the register addressing mode. Okay. So when we have this, right? So let's look at the direct mode. Okay, so we have data equal to AL and AH must be cleared, right? And then just do the division. Okay, the data 8 divide by the data 8, and then move the result. So we get the result in AL, okay, and then the remainder, okay, in AH. So we put the quotient and also the remainder. Okay. Okay, also using the register addressing mode. Okay. So like this. Okay, so how do we use the register addressing mode? So mean that we move first. Okay, we move first that number, right? So we move the data A into BH and then we divide the BH. Okay, we don't directly divide the number, divide the data. Okay, so that's the way. Okay, you have that, right? Then only you move AL, the result, into quotient 1 and AH into the remainder. Okay, so that's the way. Okay, so we can also use the register indirect addressing mode. Okay, indirect means that we put into the address of that. So over here, we put into the address of BX. So the command is this one. Okay, the data 8, which is the result. So we put that into the address of BX. Okay, into the address of BX. So once we have that, okay, once we have that, then we can, okay, divide this. Okay, we divide the data, all right, the data that we put into the address of BX, and then we divide the address of BX. Okay, to mention that byte pointer BX. Okay, and then the result is similar AX and BX. Okay, so we also have word over word. Okay, the numerator is in AX and DX must be clear. Okay, the denominator can be in a register or memory. Okay. After the division, AX will have the quotient. Okay. The remainder will be in the DX. Okay. So that's why DX must be cleared, because we're going to store the remainder in the DX. Okay, so word over word. So we have, this is a word, right? Put to AX and then we clear the DX. Okay, we put another word to BX and then we divide the BX. Okay, and then the quotient we will put to AX and remainder is in the DX. Okay. And then we have word over byte. Okay. The numerator is in AX and the denominator can be in a register or memory. Okay, after division, AL will contain the quotient and AH will be the remainder. The maximum quotient is FF. Okay, because that is what is maximum supported by AL. Okay, it's only FF. Okay, so the program, okay, so for example, we have the program divides AX, okay, 2055 by CL, which is 100. Okay, so the quotient is 20. Okay, you divide 2055 with 100. So it will be 2 0. Okay, 2 0. So you have a remainder of 55. So you have the remainder of 55. Okay, so this 55 should be stored in the AH and the 20, all right, 20 in the decimal should be stored, it should be stored in the AL. Okay, so that's the result. Okay, so we store into AL and AH. Okay, and lastly, we have double word of over word. Okay, so double word, so it can be up to the as I said, it's up to 32-bit of number, right? So we have 16 and 16. Okay, so this one should. Okay, so we have this 16-bit and another 16-bit. So that's the word. Okay, so this is how we do it. Right? So after the division, the quotient will be in AX and the remainder will be in the DX. And the maximum quotient will be FF. Okay. So you have the data 1, right? So this one, okay, and the data 1 plus 2, which is this the upper part, right? So you move that. To the X, right? Meaning that here we will contain 0, 0, 1, 0. Over here we contain 5, 4, 3, 2. Okay, so we have that, and then we divide the data 2. So with this data 2, okay, then the result will be stored in the AX and also DX. Okay. All right, so that's it for addition, subtraction, and multiplication and division. Okay, I'm going to continue with the logic instruction on Thursday, right? So that's it for today's session. Okay, so as usual, if you have any question, you can let me know. And will you please turn on your camera so we can take the attendance for today. Okay, come on everyone. Okay, I'm gonna count from 10. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, give me one more shot. All right, thank you. All right, so see you again on Thursday. Okay, Assalamualaikum and bye.
Thank you, Doctor.
Thank you,
Thank you,
Doctor.
Doctor.
Thank you, Doctor.
See you soon.
See you.
Tak ada.